Bismillah, Alhamdulillah, wassalatu wassalamu ala Rasulillah. This is section 11.3 and it's about the integral test. Well, we have seen in section 11.2 that if we have Sn, we can find whether the series converges or diverges. But in general, it's difficult to find Sn. Okay, the exact sum of the series is difficult. For telescoping sum series and for geometric series, we were able to find a simple formula for Sn, but usually it is not easy to discover such a formula. Therefore, we will start from now on develop several tests that enable us to determine whether the series is convergent or divergent without explicitly finding its sum. So we will not find their sum, but we will be able to determine whether the series is convergent or divergent using these tests. The test in this section is called the integral test. And this test has conditions, and you have to pay attention to the conditions of each test. Suppose f is a function. Suppose this function is continuous and positive and decreasing on the interval 1 to infinity. Because usually the series starts from 1, n equals to 1. So we need the function f to be continuous, positive, decreasing on the interval 1 to infinity. And an equals f of n. So there is a series, has the same definition as the function, but for integers. For n equals 1, 2, 3, 4, 5. Positive integers. Then this series, now the test says if these conditions are satisfied, then the series is convergent if and only if the improper integral of the function f of x from 1 to infinity is convergent. That's the test. So if the improper integral is convergent, the series is convergent. If the improper integral is divergent, the series is divergent. So how to use the integral test? We will be given a series. For example, this series. Test this series for convergence or divergence. And we have to look to this series and see whether it's positive. The terms of the series are positive. If n is 1, 2, 3, 4, it's clear that it is positive. Continuous, the denominator is not 0 from 1 to infinity. And we prove that it is decreasing. And then if these three conditions satisfied, we find the improper integral of the function f of x equals 1 over x squared plus 1. And if the improper integral from 1 to infinity is convergent, then the series would be convergent. If not, the series would be divergent. When we use, pay attention to this point, when we use the integral sets test, it's not necessary to start the series or the integral from 1. I mean, sometimes the series would be, or the function would be decreasing starting from 2, starting from 3, starting from 5. So you can find, if you can test the integral from 4 to infinity, from 5 to infinity, from any number n, capital N to infinity. And if you find that from capital N to infinity, the improper integral is convergent, then the integral from 1 to infinity would be convergent, and the series from 1 to infinity would be convergent. And we have seen this in section 11.2. Adding finite terms does not affect the convergence or divergence of a series. So if we add from 1 to capital N, to a divergent series, it will stay divergent, or to convergent, it will remain convergent. So here, let us check if is continuous on 1 to infinity, of course. Why? Because the domain of f consists of all real numbers, because we have no problems with the denominator. The denominator cannot be 0. F also is positive on 1 to infinity, of course, x squared. And let us discuss whether it's decreasing or increasing. To find where it is decreasing, we find the derivative. And the derivative of 1 over x squared plus 1, well, the derivative of 1 over u is negative 1 over u squared times u prime. So that's the chain rule. So the derivative would be x squared plus 1 to the power 2, okay, times negative the derivative of x squared plus 1, so negative 2x. So that's f prime. It's clear that it is positive, the denominator is positive, the numerator is negative, so it's less than 0 for x greater than or equal to 1. From 1 to infinity, the f prime is negative. So f is decreasing on 1 to infinity. So the three conditions satisfied. So now we consider the improper integral of this function from 1 to infinity. And by definition, if you need more review, more information about improper integral, check chapter 7, section 7.8. So we write it limit from 2t to infinity, integral 1 to t of 1 over x squared plus 1 dx. This is how we define the improper integral. And the integral of 1 over x squared plus 1 is just tan inverse x. From 1 to t, it's a definite integral. So this is the limit of tan inverse t minus tan inverse 1. And tan inverse 1 is pi over 4. So this is the limit of, now what is the limit of tan inverse t when t goes to infinity? Tan inverse infinity is pi over 2, as we know from the graph of tan inverse, because this is the graph of tan inverse and there is an asymptote at y equals pi over 2. So the answer is pi over 4. So the improper integrals converge to pi over 4. So by integral test, the series 1 over n squared plus 1 from 1 to infinity converges, because the improper integral converges. So the series converges by the integral test. So that's the integral test. Of course, in order to use the integral test, we need to be able to evaluate this integral, okay? And therefore, we have to be able to find an antiderivative. Frequently, this is difficult, okay, or sometimes impossible. So in the next sections, we will develop other tests for convergence. Now, because integral, we have taken this in section 7.8, integral 1 over x to the power p from 1 to infinity dx. This integral is converges for p greater than 1 and diverges for p less than or equal to 1. So because of this, and 1 over x to the power p from 1 to infinity is positive, decreasing, continuous, because the domain is from all real numbers except 0 and 0. We have no problem with 0 because we start from 1 to infinity. Uh, this is if p is greater than 1. Okay, so the p series summation 1 over n to the power p would be convergent for p greater than 1 and divergent for p less than or equal to 1. And we will call this series 1 over n to the power p, we will call it the p series. And we will use this series a lot in the coming sections. So it is okay to say that this, when we ask it about this series now, 1 over n cube, it is okay to say that this is a p series with p equals to 3 greater than 1. So it is convergent, just like this. You don't have to prove that it is convergent because we know how to prove it is convergent. We, from the improper integral 1 to infinity 1 over x to the power 3, and we know that the improper integral converges. So the p series converges for p greater than 1. While if I ask you about this series 1 over n to the power 1 over 3, so you say that this is a p series with p equals 1 over 3 less than 1, so it is divergent. So from now on, we would like to know or see the p series immediately. If we just see a series, is it a p series or not? And we recognize it. And we know that it's convergent when p is greater than 1 and divergent if p is less than 1, less than or equal to 1. Now, another important note, look here in this example. We know that this improper integral, we found out that this improper integral converges to pi over 4. But I wrote only the series converges. I did not say converges to what, because actually we don't know the sum of this series. I mean, I did not evaluate the sum. The sum is not easy to find. So, for example, also the improper integral of 1 over x squared, we have seen that this is equal to 1 in section 7.8. So what do we conclude from here? We conclude that the p series, this p series converges. But is the sum of the series equals to 1? No. In fact, it has been proven that the sum of this series is pi squared over 6. So they are different. The sum of the series is not equal to the improper integral. If they converge, then they converge to different values. This is an infinite area and this is an infinite sum. So they are not necessarily equal in general. Determine whether this series is converges or diverges. So let us talk about the function f of x equals ln x over x. What is the domain of this function? The domain is from 0 to infinity. 0 is not in the domain, and the domain of the logarithmic function from 0 to infinity. So f is continuous, positive, on the interval from 1 to infinity, because 1 to infinity part of the domain. And it is positive because the ln, the logarithmic function, after 1 is positive. All right, so just let us prove that it is decreasing. So let us find the derivative. X squared using the quotient test, quotient rule. Derivative of ln x is 1 over x times the denominator, which is x, minus the derivative of x is 1 times ln x. X over x is 1, so the derivative is 1 minus ln x over x squared. X squared is always positive, and 1 minus ln x would be negative, so 1 minus ln x is less than 0 for len x greater than 1. If len x is greater than 1, 2 or 3, then 1 minus len x would be negative. If you raise both sides to the base e, so x is greater than e to the power 1 or e. So if a prime is negative for x greater than e, so f is decreasing for e from e to infinity. Okay. Well, e is 2.7. So I can start the integral from e to infinity. The integral of len x over x dx, the improper integral. It's okay to write, to include the e, okay? So this is the limit when t approaches infinity, e to t len x over x dx. Now, how can we evaluate this integral? If I take u equals len x, then du would be 1 over x dx. So this integral would be integral of len x is u and 1 over x dx is du. And the answer would be u square over 2. And u is len x square over 2. So now this is limit t goes to infinity. And the integral of len x over x is len x to the power 2 over 2 from e to t. And now this is equal to limit t goes to infinity of len t square over 2 minus len e is 1, so minus half. And now if t goes to infinity, then len infinity is infinity because of this graph of len. Len infinity, infinity square, infinity over 2, infinity minus half infinity, so the answer is infinity. So the integral diverges. So the series len n over n from e to infinity diverges by the integral test. So the series from 1 to infinity len n over n also diverges. Some exercises. Use the integral test to determine whether the series is convergent or divergent. So let us consider the function x squared over e to the power negative x cubed. Well, it is negative here, so when I bring it down, it would be positive. This function, e to the power x cubed is always positive, x squared always positive, no zeros. So the domain of this function, all real numbers. So f is continuous and positive from 1 to infinity. And let us check the derivative to find where it is decreasing. So the derivative is, well, I can find the derivative using the product rule. So it is x squared times e to the power negative x cubed. I'll find this formula instead of finding the quotient rule. They are the same anyway. So the derivative of x squared is 2x times e to the power negative x cubed plus x squared times the derivative of e to the power negative x cubed which is the same, times negative 3x squared. To write f prime in its easy form, it's in simplest form, I take x e to the power negative x cube as a common factor. So I have 2 here. Then there is a negative 3 here. I took x, so I have x times x squared, that's x cube. And e to the power negative x cube has been taken, so that's it. So I can write f prime as e to the power x cube, and here x times 2 minus 3x cube. Now, this is always positive. The denominator is always positive, so the sign depends on the numerator. The x0 is a 0 of the numerator, but from 1 to infinity it is always also positive. I'm considering only from 1 to infinity. So here this function 2 minus 3x cube, 2 minus 3x cube would be negative, okay, when or if 3x cube is greater than 2. If 3x cube is greater than 2, then 2 minus 3x cube would be negative. So this means that x cube is greater than 2 over 3, or x is greater than cube root of 2 over 3. If I use the calculator to find the cube root of 2 over 3, that's 0.87. So for x greater than 0.87, f prime would be negative. So f prime is negative, hence f is decreasing. For 0.87 to infinity or from 1 to infinity. So I can use the integral test and find the integral from 1 to infinity of the function x squared over ex cube dx. And this is, as usual, the limit of this integral 1 to t when t approaches infinity, x squared e to the power x cube dx. And the question now, how to evaluate this integral? The indefinite integral of x squared over ex cube. Well, if you take u equals x cube, then du is 3x squared dx. And then this integral, I need 3x squared dx. So I divide by 1 over 3 outside. It would be changed to du over eu. So this is 1 over 3, and this is e to the power negative u, and the integral of e to the power negative u is e to the power negative u over minus 1. Or in fact, I could have raised it up a to the power negative x cube and take negative x cube as u. It would give you the same. So the answer at the end is negative 1 over 3 e to the power u, and u is x cube. So that's the integral. So we will have limit t approaches infinity of negative 1 over 3 ex to the power 3 from 1 to t. And this is the limit when t approaches infinity of negative 1 over 3 e to the power t cube minus negative 1 over 3 to the power e to the power 1, so 3e. Now, if you replace t by infinity, t cube is infinity, cube infinity, e to the power infinity is infinity, because the graph of e is like this. So negative 1 over infinity, this would be 0. So minus times minus, the answer would be 1 over 3e. So this integral converges to 1 over 3e. So by the integral test, the series, if I call this an, so the series an from 1 to infinity converges. Another question. Let me tell you something. As we have seen, the use of the integral test is not that easy. So I'm giving you here in this remark two series frequently given in the exercises and the convergence conditions for this series. So this series is convergent for p greater than 1, and this series is convergent for p greater than 1 also. These series usually their convergence is proven using the integral test. So if the question is contains one of these series, you should immediately try to use the integral test, not other tests. But for other questions, you may use some other tests. So here, the example we need to solve 1 over n ln n to the power 3 is convergent according to this remark. It is 1 over n ln n to the power 3. It is convergent. And the one we just solved, ln n over n, or the one before, when p is 1, it is divergent. And we have seen that ln n over n is divergent. We proved it here. Okay. So let us prove the convergence of this one. So when I see this form, I immediately use the integral test. Although he said also in the question here, use the integral test. So I consider the function 1 over x times ln x to the power 3. And again, the domain of this function is from 0 to infinity. So 1 to infinity is in the domain. So f is continuous, positive, from 1 to infinity. And let us find the derivative. I will use the formula we just wrote for the derivative of 1 over u. So I will have x squared and ln x to the power 3 to the power 2, so that's to the power 6, and then negative the derivative of this. And to find the derivative of the denominator, I need to use the product rule. So derivative of x is 1 plus x times the derivative of ln x to the power 3, and the derivative is 3 by quotient rule times the derivative of ln x, which is 1 over x. So this x cancels with this x. And I can take ln x as a common factor. Already minus here is a common factor. So even not ln x, I can take ln x squared because I have ln x to the power 3 and ln x to the power 2 here. So I still have ln x. And here I have x cancels with x, so I just have 3. X squared ln x to the power 6, these are always positive. Ln x squared is always positive. So the sign depends on negative ln x plus negative ln x minus 3 if you want. So if ln x plus 3 is positive, then f prime would be negative because of this sign. So f prime is negative if ln x plus 3 is positive. This means that ln x is greater than negative 3, or x is greater than e to the power negative 3. And e to the power negative 3 is a small number. It is 0.05. So if ln x, if x is greater than 0.05, then f prime would be negative. So f is decreasing on 1 to infinity. Although he said here 2. The series starts from 2, so everything, of course, if it is continuous from 1 to infinity, it would be continuous from 2 to infinity also. So I can talk now about the integral, the improper integral from 2 to infinity of the function 1 over x times ln x to the power 3. And it is the limit when t approaches infinity of the integral from 2t to t 1 over x ln x cube dx. And how to evaluate this integral, the indefinite integral 1 over x ln x to the power 3. I take u equals ln x. So du would be 1 over x dx. So this integral would be 1 over u cube du, because 1 over x dx is du and ln x is u. So it's u to the power negative 3. The integral is u to the power negative 2 over negative 2. So the integral is negative 1 over 2, and u is ln x to the power 2. So this would be the limit of negative 1 over 2 ln x squared from 2 to t. So I have negative 1 over 2 ln t all square minus ln 2 squared. Now ln infinity is infinity, infinity square infinity, infinity, negative 1 over infinity is 0. So the answer is positive 1 over 2 ln 2 squared. So the integral converges, and by integral test, the series also converges. If I call this an, then the series is convergent. And I'll stop here and solve more exercises about the section in another video.